So something very interesting happened in my office the other day. You see, one of the people from my marketing department goes to his boss and says, "Hey, this ad we're running, instead of the word health, can we use the word fitness? I think it will convert better." And the boss said, "Well, that's an interesting hypothesis. Let's test it out." Right? So a lot of times we come up with opinions. We think that, having this policy implemented, or, this new thing in the house, or this thing that you buy will improve your life, or will improve the climate, or something awesome will happen, or this drug is going to work. And these are all hypotheses, right? And until we prove it, and until we say that this is better than the existing solution that we have, there's no way for us to know whether what we're doing is correct or wrong or even related in any way. So the idea with hypothesis testing is that we are actually able to differentiate and say that what we're doing is better than what we used to have, and not because of some random chance, because like I mentioned, random chance is a very important player in this. So let's get right to the episode. Righto, so hypothesis testing. The formula for data-driven decision making is that you formulate a hypothesis. You say that, look, I think this is how this new drug is going to affect people. And then you find the correct test. You say, okay, we have to compare it to the old drug or whatever test is relevant. Then you execute the test. You actually go out, give the drug, get the surveys done. And then finally, after you collect the data, you make a decision, right? This is the data-driven decision-making model. Now, what is a hypothesis? Any statement that can be tested is called a hypothesis. If it's not testable, it's a useless hypothesis. We don't even call it a hypothesis. So a bad hypothesis could be something on the lines of onions in India are expensive. Now that doesn't mean anything. What does expensive mean, right? Does it mean that onions are too expensive? Does it mean onions are expensive with respect to tomatoes? Does it mean that onions are generally expensive compared to the price of everything else? What does it mean exactly? So a good hypothesis for the same thing is onions in India are more expensive than 30 rupees per kilogram, right? Or cost more than 30 rupees per kilogram. That's a good hypothesis because you have a data point to play with, right? So I'll give you some more examples. Is it right to make a statement such as Spider-Man is better than Batman? Right? The first question that most of you would ask in such a situation is based on what? Right? Is it strength? Is it speed? Is it punches per second? Is it ability to web swing? So it really depends on in what dimension. You need a dimension to play with. So hypotheses need specific numeric data points on a particular dimension, right? And you'll understand this in a bit. So I'll give you an example. Glassdoor is a website for salary comparisons and job reviews, right? And it has this estimate for the average salary of a graphic designer in Bangalore. So on Glassdoor, a lot of people come in, they self-report their title. They say, hey, I'm a graphic designer and I make this much money. So Glassdoor has kind of averaged the entire thing out. Now, suppose we went out and surveyed 1,000 random graphic designers in Bangalore to test whether this number is correct or not. And 1,000 is our sample size here. Glassdoor has maybe a larger sample size or a smaller sample size. We don't know that for sure, right? But we are going to go and sample or survey 1,000 random graphic designers and see if the average number we get is similar or different from the Glassdoor number. So we have this original hypothesis. It's called the null hypothesis, and that's the current hypothesis that Bangalore graphic designers are paid on average 4.43 lakhs per year, right? This is the data we currently have. We denote the null hypothesis by H0, right? This is just notation, right? The null hypothesis is called the status quo. It means this is what it currently is, right? This is what the data has currently said. The alternative hypothesis, denoted by HA, also called the challenger hypothesis, is the hypothesis that says that graphic designers are not paid an average of 4.43 lakhs per year. Maybe they paid more, maybe they paid less. All we're saying when we're testing an alternate hypothesis is that, look, whatever the current hypothesis is, it's wrong, right? So the H0, and we can it's denoted by H0 colon U0, this is just denotation, is 4.43 lakhs per year. And HA, which is the alternate hypothesis, is not equal to 4.43 lakhs per year, right? It's just this, we have just two statements. One we know is the current statement, and one is a statement we are trying to prove. We're trying to say it's not 4.43 lakhs per year. So we accept the hypothesis if mu0, right, is close to the true mean mu. For example, when you go and do your survey, if your data shows that the mean is 4.44, which is quite close to what H0 is, it's a little higher, then it's very close, so we say we'll accept it, right? Glassdoor. So maybe it's if there was a completely different set of graphic designers. So maybe if one or two graphic designers were slightly different who came on Glassdoor and put their data in, maybe we'd get similar numbers. So this was random error. It just depended on which graphic designers, maybe a few graphic designers who put some different data or, who are outliers. So for example, if your data shows that the mean comes up to be 4.44 lakhs per year, that's close. So you accept it. You say, this could have been random chance, and you reject. And you say that the null hypothesis is rejected and the alternate hypothesis is true if your data is too far away from the true mean mu, right? So, for example, if your data shows that the mean is 7 lakhs, say you did your survey from 1,000 graphic designers, and most graphic designers are saying, my salary is 6.5 lakhs, 7.5 lakhs, 8 lakhs, and the average comes out to 7 lakhs, that is too far away, right? So you reject the null hypothesis and you say the Glassdoor data is wrong. Right? And the data from my sample size says that the true mean is 7 lakhs and it's not 4.43 lakhs. So I'm going to reject the null hypothesis, and my alternate hypothesis is now the fact that the mean is 7 lakhs, right? And that becomes the new null hypothesis for the next person to either, challenge or accept. So I want to introduce you to a concept called the p-value, right? And the p-value is simple. Suppose somebody came and asked me, Varun, how accurate do you think the Glassdoor data is? How accurate do you think the null hypothesis is? And if I say, I can choose any number between 0 or 1, and you can go into decimal places to say how accurate I think the null hypothesis is. I'm going to say, look, I think the Glassdoor data is very accurate. I think the p-value is 1, right? Which means that if you repeat the experiment 100 times, in all 100 situations, you will land up exactly at either 4.43 or some number very close to 4.43 lakhs, right? Because here's the thing. If I went out to survey 1,000 graphic designers, right, I might get some average. But tomorrow, if I surveyed another 1,000 graphic designers in the same place, I might get a slightly different value, right? And the reason for this is because some graphic designer might be sick, right? They might not come out and give the survey. Some guys, they might have just changed jobs, so their numbers would be different. So the p-value essentially is how repeatable is this? So if the p-value is 0.1, it means that if we repeat the experiment 100 times, the null hypothesis, which is the fact that the average salary is 4.43 lakhs, will be true just 10 times out of 100. And this means that 10 out of 100 times we conduct this survey, and if we conduct this survey 100 times, then 10 times the mean you will get on paper is 4.43 or somewhere close to that number. And the other 90 times, it will be far away from that number. So if we repeat the experiment 100 times, 90 out of 100 times, you will get a number which is 7 lakhs or 8 lakhs or 2 lakhs, which is the average, which is very far away from that null hypothesis. If the p-value is 0.4, it means that if we repeat the experiment 100 times, the null hypothesis will be true 40 times, right? Which is a big number. It means that almost 40% of the time, you will see that 4.43 average show up or somewhere close to that. Right? If the p-value is 0.05, it means that if we repeat the experiment 100 times, the null hypothesis will only be true just 5 times. So we're saying that, look, most of the time you are going to get some number that is very, very far away from that 4.43 lakhs. And this is important because the lower the p-value, the more accurate your alternative hypothesis is. Right? So whenever you do any test, the researcher decides the p-value, and we'll come to what that means in a bit, but the p-value is pre-decided before the test. It's like a cutoff value. Right, so the next thing I wanted to introduce you to is the Ttest. The Ttest basically it's very simple, right? You compare the mean of your survey with the mean of that Glassdoor survey, right? Or any two different groups, you compare the mean or the averages of those two groups. So the Ttest is, in our case, we went out and we did a survey of 1,000 graphic designers. And we found that our study's mean was 3,30,250, right? And that's much lower than what the Glassdoor study mean was. And the Glassdoor study mean was 4,43,843, as we already know. The Ttest compares the mean value of two groups and then compares it to something called a significance level, which the researcher sets. So the researcher says that, look, we are looking for at least this much variance or this much variance, or we need at least this much variance to say these, this is not random chance. Because say your study's mean came up to 4.42 lakhs. That's quite close, isn't it? But if the researcher sets a significance level that's really low, then in what happens in that case is that the study would still say that, look, the Glassdoor study is wrong, right? So the significance level is very important, and there are some standard values for this, right? So in our case, if the p-value determined from this test is 0.03, only 3 out of 100 times the null hypothesis, which is the statement that the average Glassdoor salary for graphic designers is 4.43 lakhs, is true, right? So we have to figure out the p-value. If the significance that the researcher set was 0.05, right, and the significance level that the researcher sets is something that the researcher decides on, and usually this is denoted by the symbol alpha, and 0.05 is a standard value, right? A lot of researchers use 0.05. Then, because 0.03, which was our p-value that we got from the test, is lower than 0.05, then we should reject the null hypothesis. That is, the Glassdoor study is wrong and your results are statistically significant. Remember, in the first episode, we spoke about statistically significant. We said that data is useful and different from the original data and not due to random chance of you surveying particularly less earning designers. If the researcher set the significance level to 0.01, that means just 1 out of 100 times the null hypothesis is true, then we would not reject the null hypothesis. We would say, look, the p-value is 0.03. We've set a significance level of 0.01. 0.03 is not lesser than 0.01, so we are not going to reject the null hypothesis, right? You're looking for very, very small variance when you go down to 0.01. So let's assume there are two medicines. I want to give you another better example of this. One is Stronger Ball or a placebo. Stronger Ball is supposed to increase muscle mass in the thigh muscle, right? If you give Stronger Ball to somebody, they suddenly become stronger in the thigh muscle, right? Or their thigh muscle gets bigger. 2 sets of 30 patients each are either given Stronger Ball or placebo for 1 month. And placebo, as you guys know, is basically a sugar pill. It has nothing in it. The question is whether the difference between the groups is statistically significant or not, right? So we're trying to prove that Stronger Ball has some effect on human beings compared to placebo. The null hypothesis H0 in this case is Stronger Ball is no different than placebo when it comes to muscle mass gain. We're basically saying there's no difference between the two because we haven't figured out any difference. And that's the thing, right? The null hypothesis is, if you guys are confused about what to place the null hypothesis, just say what we currently have works perfectly, or what we currently have or what we're testing is exactly the same as before. Right? You have to have that. The alternate hypothesis, HA, is that Stronger Ball is indeed different than placebo when it comes to muscle mass gain, right? We're actually saying that Stronger Ball has a difference. So let's look at it. So maybe this survey was conducted or the test was conducted, and after a month, thigh was cut off and it was just put on a measuring device, on some sort of weighing scale, right? Obviously, that's not going to happen, but assume there was a way to measure how much muscle mass was put on the thigh muscle. So the Stronger Ball mean muscle mass increase, that means the average increase in muscle mass, was 1.2 pounds. And the muscle mass increase for placebo was just 0.82 pounds. Now the Ttest compares the mean value of two groups and then compares it to the significance level which the researcher sets. We already know this. In this case, suppose the p-value determined from the test is 0.0002. Only 0.2 times out of 100 times, that is just 2 times out of 1,000 times, the null hypothesis, which is the statement that Stronger Ball is no different than placebo, is true. That means that, if the p-value determined from the test is that low, it just means that, dude, Stronger Ball works. If the p-value threshold that the researcher set was 0.05, then because 0.002 is lower than 0.05, then we should reject the null hypothesis that Stronger Ball and placebo are the same. That means we are claiming the alternative hypothesis, that is Stronger Ball is different than placebo, is true. That is, this observed change in muscle mass is not due to random chance. Stronger Ball actually works. And that's what the alternative hypothesis is about. We're trying to prove that whatever test or whatever drug or whatever change in the landing page that we're doing actually is different from what was already there and not because of random chance. If the researcher set the p-value threshold at 0.01, then we would still reject the null hypothesis. Even if you said, we're going to be very stringent and 1 out of 100 times is what the p-value we're looking at, even then we would reject the null hypothesis because the p-value determined from the test is really low. And obviously I haven't taught you how to determine the p-value, right? You don't actually repeat the test 100 times or 1,000 times. There are methods for this, and we don't need to get into how we determine the p-value, and you have tools for this, but the p-value essentially allows you to figure out from the test itself. There are ways, and if you guys want to know how to determine the p-value, I've attached a document to this video. It's in the resources section where you can actually figure out how to determine the p-value. It's, you can use a tool to do it as well, but you get it out of the data itself, right? So I'll give you an example of a simple real world study, right? And in this study, and I just picked this off of a place called PubMed, which is a place where I look at research studies. In the study, men with liver disease and low testosterone were given testosterone via injection of placebo. For people who don't know what testosterone is, it's steroids, right? It's for what bodybuilders take to get bigger. So at study completion, the appendicular lean mass was significantly higher in testosterone-treated subject with a mean adjusted difference of 1.69 kgs increase, right? The p-value of this test was 0.021, and this measured from the data itself. It means that if the same experiment was repeated 100 times, only 2.1 out of 100 times, the null hypothesis, that is, the testosterone group is no different from placebo group for muscle mass increase, will be true. 97.9 times out of 100, testosterone group will be different from placebo group. So testosterone actually works. We use p-values and significance levels to avoid factors like random chance, which is a very common occurrence in most studies. Now you might think, why are we going through all of this effort just to erase random chance? And that's because random chance is such a big factor in everything we do, right? We cannot make conclusions out of data because of things like random chance. Say you gave two people some drug, and they went out, and you after 8 years you went and asked them, okay, have you lost weight because of the drug? And somebody comes in and says, yeah, I've lost weight. Now our question is it because of the drug? Is it because of that person's lifestyle? What are the different factors, right? So our job is to try to keep those factors at bay, right? By repeating the study, by seeing if it was random chance, whether it was external factors that caused this increase or decrease in chance. So that's what we're trying to do, right? We're keeping the other variables at bay. We are trying to avoid random chance. And that's why we go through all of this effort. Because a lot of the data, a lot of the studies that come out these days, they're all random chance. If you took a different set of audience, if you took 100 other people, you get completely different results. You get actually completely different results. So take an example of the number of hours you sleep per night. So if I came to a particular school and I asked all the students, how many hours do you sleep per night? And they gave me some value. And, I interviewed 100 students and my average value was 7.5 hours. Say the next day I went, instead of section A, I went to section B and I asked them the same question, right? I take 100 students and I ask them, how many hours do you sleep per night? I would get a slightly different answer. Maybe I'd get 7.2 or 7.7, right? But if I got 15, but if I got a completely different number, like say 4, then I'd know, hey, something very different is going on with this class. It's probably not random chance. And we need to look at the p-value for this, right? So, but in most cases, if you went to a school and asked 100 students in each section and you went to 10 different sections, how much the average amount of sleep they got, you would find that those values are very, very similar. So you get 7.5, 7.7, 7.2, and you'd be like, okay, all of these, they're the same sample size, right? That's basically the point of doing this. And p-values and significance levels allows us to basically say, okay, something's going wrong with this class. Maybe it's section C, maybe, in a section, say section Z, right? The average is now 4 hours, whereas all the other sections, the average is 7.5. Then we can specifically say, dude, something is going wrong with this class, right? There's something very specific to this class that's giving them issues. Maybe if you repeated the test after 2 months, you'd find that their sleep was normalized and it was just a random chance. Maybe you specifically came to them when they had an exam, right? And then what you try to do is you try to say that, look, I think it was the exam that caused the lack of sleep. And that's what we're essentially trying to do, right? We're trying to build real correlations instead of just random stuff. So a good test must be reproducible with the same results on multiple occasions, which means that you want a low p-value. You want the null hypothesis to only show its head very rarely. You need to have a large sample size. The larger the better, with diminishing returns. And you need a low risk of bias, which means you need to try to get diverse sample sizes. If, for example, you're looking for specifically, if you're looking for people who sleep, how many hours of sleep somebody gets, if you go to CEOs, you'd find that they sleep much lesser than if you went to, say, people who had no jobs, right? So trying to get a diverse sample, some CEOs, some unemployed people, that's more important than you going to a specific group, unless you're testing that specific group. And there are other things you can do, like blinding. For example, if you're giving two people a drug, if you've written the words stronger ball on one of them and placebo on the other of them, then obviously the people are going to know which is which drug, and their behaviors change because of it. So you need to blind people. You need not show them. So, and before we go to the other types of tests, I want to show you something very important, right? So if we go all the way back at this Glassdoor study, I want to tell you that a lot of people, especially newspapers, they take out salary data from Glassdoor. But I wanted to see something very important here, right? The number of salaries here is just 85. 85 is a very, very small sample size, right? And for a lot of newspapers to use Glassdoor as a reference with sample size of 50, 80, 100, it's just silly, right? Because, and this is mostly because very experienced graphic designers, they wouldn't go on Glassdoor and update their salary. They just don't care about that. Most of them have multiple projects. So you should really, when a newspaper takes this data and just states it and everybody shares it on Facebook and says, look, the average salary of graphic designers is 4.43 lakhs, that is a problem, right? You need a bigger sample size. You need somebody conducting larger research sets. But hey, some data is still better than no data because at least you have something to work with, right? But in general, bigger sample sizes, accurate data. Do not share stuff on Facebook that have really small sample sizes like 10 or 15 because that's pointless. It is not representative of the entire population. Right, so let's get back. Just like we did the Ttest, there are other types of tests. There's the Ftest, there's Ttest, there are things like ANOVA, which is analysis of variance, especially if you want to test more than two groups. So we're not going to go in through all of that, right? The point of this course is not for me to bore you. It's for me to tell you that there are ways to compare groups. There are different ways to compare two groups. If you want to compare, say, the stronger ball group with the placebo group with, say, another group, which is stronger ball plus testosterone, right? Then you have to do things like ANOVA, right? So we're not going to talk about all of that, but I just want to let you know that they exist. Right. So this was a slightly long episode. Hopefully we've broken down into chunks, but the idea is that we're trying to eliminate random chance, right? And that's what this entire episode was about. And when we change a small word in an ad set, or when we, make a landing page with a slightly different sign up button, what we try to do is we try to compare it with the old page, right? We say, let's just assume at the null hypothesis that there's no difference between these two pages we've created. And then what we try to do is we try to prove that the alternate hypothesis, which is that the two pages are somehow different in their conversion rates, we try to prove that, right? And most of the time, you'll be very surprised, most of the time people fail. Right? People just fail. Or most of the time, the null hypothesis holds true, right? At least in the case of landing pages, you can make a change, but it doesn't change by much. And you'll find out if you have a decent significance level, the p-values are just, they don't make sense, right? It doesn't make sense for us to change the entire landing page to the new one because we can just claim that, look, this was random luck. So that's that, right? We're trying to eliminate random luck. So the decisions we make are real decisions and are happening because of what we did. So that's it for this episode. Catch you on the next.